here's a number line, and person A says the truth is right there. This is the value of all goodness, and I'm pretty confident. Here's my error bar. Basically, I know it's greater than this one and less than that one. It's in this range, but I say it's right there. This is the mean of my estimate with plus or minus that amount. And person B says, no, you're wrong. It's right here. And my error bars are like this, plus or minus that amount. And then your job is to come to the final conclusion of where is the truth. I don't even know what I'm talking about. Some number on a number line. But what number do you pick?
Well, how trustworthy are the two sources?
Well, they've given you their trustworthiness in the form of error bars, but yeah. Let's pretend we believe they're error bars. I guess. I think you'll agree with me. It's probably around here-ish. Okay. Cool, but now how do you do that mathematically and optimally? And don't try too hard to answer it. It's an impossible question because professors ask impossible questions. There's no way to compute that value. We all feel it's about here, but the thing is there's not enough information here. But what I do want to show you is now let me give you enough information. Suppose they give you probability distributions and pretend I'm good at drawing perfect Gaussian, perfect normal distributions. You see what I'm getting at. Pretend those are nice, smooth curves. Now we have two distributions, and I want the answer of, okay, where is the real mean?
Like the joint distribution and finding mean.
Yeah, is joint the right thing? I think it is. Yeah, it is the joint. And now all of a sudden the problem becomes really easy because we can say to ourselves, a continuous is hard to reason with, so let's just pretend we had categorical distributions and solve the problem first. So this person says it's there and there and there and there and there, 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 there and there and there, there, there. And then this other person says, no, it's kind of like this. Not a very good approximation, but pretend these bars kind of fit inside those distributions. If we were doing that, then it's really the same thing as this coin flipping problem. We can very well say, hey, the product of these two values is the probability of that value. The product of these two values is the probability of that value, etc. And all of a sudden we have numbers all along this discretized number line that give probabilities of the answer. And then we could sweep over it again and find the maximum one, and now we would know probabilities for the joint distribution, and we could say the answer is right there. We can do that with continuous distributions as well. Basically, we just multiply them together, by which I mean each point, the probability at each point, we want the product of those points. And whatever that product is, whatever distribution comes from multiplying these distributions together, is the distribution of beliefs that should follow from beforehand. Do you agree that that's pretty obviously true at this point? Okay, the big moral of the story is distributions give you a lot of information, a lot more than just confidence intervals, a lot more than here's my mean and here's how sure I am. Because distributions say everything you need such that you can, basically there's no way you could express any more information than what you have in a probability distribution about one specific thing. This one specific thing is how likely is it to be here and here and here and here and all those different places, and this is a full set of information. So don't underestimate the vast quantity of information in a probability distribution. Okay. A lot of people really like the normal distribution. There are several reasons for that. Are you familiar with the central limit theorem? Okay, anybody not familiar with the central limit theorem? It's okay if you're not. Okay, well, suffice it to say, if you take a whole bunch of noisy stuff, if you take a bunch of probability distributions and you aggregate them together, the average distribution tends toward a normal distribution. In other words, if you go into a football stadium and somebody starts talking to you, hey, how you doing? It sounds like words. If everyone in the darn stadium starts talking, what does it sound like? All right. If you listen to a specific radio station, you hear, welcome to CJKNN, live from so-and-so, right? If you tune it to somewhere else where you're hearing noise from the sun and radio waves bouncing off walls and everything coming together into your radio, if you even remember when we had radios that could do this, that didn't actually generatively, adversarially tune to the nearest valid station, it sounds like, right? And what does that sound? Well, it's me opening my mouth and pushing spit through, because that makes whole sound waves bounce off the walls of my mouth in a whole bunch of different ways, and the spit munges it in lots of ways. The point is, that's called white noise. It follows a Gaussian distribution. Everything follows a Gaussian distribution when there's enough complexity all added together. And so statisticians love to assume things are Gaussian, because that just means pretend we live in a complicated world. And if things are sufficiently complicated, everything tends towards a normal distribution. Mathematically, there's another nice property of normal distributions. The product of two normal distributions is a normal distribution. You see why that's useful? Let me prove it. I know this is kind of overkill, but this is going to come up really soon, so I think it's worth making sure we believe it. Here's the equation for a normal distribution. That looks kind of nasty, doesn't it? It's not as nasty as it looks. First, let's just identify parameters and variables. What are parameters and what are variables? Parameters are the things we tune to change the function, right? Or in this case, the distribution. Variables are the things we pass in order to get output. There's only one variable in here. It's right there. It's an x. Okay? Well, how many parameters are there in the normal distribution? Two. We've got sigma, which means deviation, and lowercase sigma means deviation. And lowercase sigma squared means variance, right? And we have mu, which stands for mean, because mu starts with a mu sound, and sigma starts with a sound which has nothing to do with variance. Why is deviation sigma? I feel like I used to know that, but I can't seem to think of why. Okay, no matter. Pi is a constant, 2 is a constant, 1 is a constant, e is a constant. Basically, now you know all the parts of the normal distribution. Okay, let's plot this thing. I want to see them both at the same time. Okay, you go where I can see the equation, please. You come over here, and we'll do 1 over square root of 2 times pi times, what should our first deviation be? 1. Great, that one's easy. Times e to the, let's see, x minus, what should our mean be?
You have to square that.
Let's put this one at -1, so we'll do x plus 1. I'm going to have to square it, so I'm going to need a parenthesis squared divided by 2 times 1 squared. So that's just going to be the same as 2. Okay. Behold a normal distribution with a mean at, standard normal distribution with a mean at -1. And you see the height comes to about about 0.4, which is what we said it was. Okay. Let's do one more normal distribution, and we'll shake up the values here a little bit. How about for the deviation here, we do 0.3. Sound good? Okay, that means I need this divided by 2 times 0.3 times 0.3. And let's put the mean at +1 here. See if I did that right. Okay. We now have two normal distributions. They have different deviations, they have different means, and I think given this information, where would you say, so person A says this, person B says that, and their distributions correctly represent how their beliefs, and you trust their beliefs explicitly. Or, in other words, these distributions correctly represent your beliefs given only what they say individually. Now that they've both spoken, what should your beliefs be? Given that the joint probability distribution represents what we want.
Just multiply the two functions together.
Yeah, just multiply those together. So I guess what I'm trying to do is test your intuition. What do you think the resulting curve is going to look like? Twink, it's right there. And here's the funny thing, it's no longer normalized to sum to 1, or to integrate to 1, therefore this is not a true probability distribution. What I'd have to actually do is find the constant of the normalization constant and divide by that. Since I don't know what it is, let's just scale it up a little bit. Let's make it 10 times bigger. That almost sums to 1. It's probably a little bit more like that. We'll go with that. Let's say that's the answer. Pretend it's normalized to integrate to 1. How do you feel about that? Can you see that it's actually sensical? I mean, whether you see it or not, it is sensical. This is the right answer. The reason that's the answer is this guy on the right, his deviation was less, right? In other words, that guy on the right was more confident about where the value was. The guy on the left, I don't know why I'm calling them guys, they're distributions, was less confident about where they were, and it turns out you're supposed to lean to the one that knows what it's talking about a little bit more. So, general life lesson there. What would happen if we were to sum two distributions rather than multiply two distributions? Then it would become a very complex distribution. It would fit over the humps of both of them, right? Well, that's not very helpful. The nice thing about a normal distribution is the mode is always equal to the mean. There's only one mode, and it's always the mean. And there's just a lot of properties that make math really nice, and it's a very natural distribution, so we like the normal distribution. Okay. So Kalman comes along and decides to solve this problem. He says, hey, where am I? Trying to get the right picture. That's not the one I want. I will close it. That's the one I want. Let's see, this is 1960s, maybe his 50s, I don't know when he did it. NASA wanted to put, let's see, 1969, isn't that when we put somebody on the moon? I think so, okay. So NASA wants to put somebody on the moon, but this is a long time ago. We haven't solved all the problems we have today. Do you see how the Kalman filter might come into play? So your rocket ship is in space, and you know where you are in space. You know your velocity and your trajectory, and you need to fire you need to send some fuel to your rocket and send a little burst of information to it. The problem is rockets they don't do exactly what you say. I mean, we know what fire does, we know about thrust, we have a model of what is going to happen to this rocket if you burn for so long. But what if you hold down the button too long? Hopefully it was computer controlled by then. But there's some noise, some variance in the rocket going exactly where you say. Because after all, it's fire. It might burn not entirely uniformly. The physical things just don't respond the way you want them to, right? So if you were here and you say, go there, you're probably not exactly where you think you are. Okay? Another thing they have to work with is, hey, there's this big, bright, round orb in the sky called the moon, and we're looking at it, and that's where we're trying to go. Pretty much that's a great way to guide your directions, isn't it? Except it turns out that they had to measure where the moon was based on a whole bunch of things. They didn't have quite as precise of instruments as we do. And there's also stars all around. There's some possibility that you're actually looking back at the Earth. You certainly don't want to fly into the Earth. I don't know what would have caused noise in the observations, but it turns out they couldn't tell exactly where the moon was. Maybe it was in measuring the angles toward the moon. So suppose you have some probability of certainty that the moon's over there, and based on where the moon is, you can tell where you are. Oh, here it is. You have to triangulate yourself. Suppose you're way up in the sky. What do you have to work with? Well, you can tell where the moon is. You can send radio waves back down to Houston. They can measure the angle to your rocket, but it's still kind of hard to pinpoint yourself exactly in space. Okay, so they had to solve this problem, and the Kalman filter was the answer. The reason this comes up in an AI scenario is it solves the problem between if you know where you were and what you did, what's your state, and if you know what you see, what's your state, and it seems to solve those types of things really well. So that gets represented in our problem with when we start doing these noisy observations. So here's noisy observations, and I press to the left, and it doesn't actually quite go where I tell it to go. I'm just pressing left over and over. If we could still follow that blue dot, then we'd understand what's going on. And I claim humans are amazingly good at this because we know what's going on in the world, even though this world is crazy chaotic, isn't it? I mean, there is so much going on around us, and yet somehow we still manage to keep our bearings. We still manage to choose actions that do useful things. Therefore, this approach, if we could solve this problem of figuring out where the dot is despite our observations being noisy and our actions being noisy, then I claim we could probably be effective at estimating our state. Okay. I think that's more than sufficient motivation for Kalman filter. Now let's start looking at how the darn thing works. 3 minutes. Oh boy, that's not going to work so well. So, assignment 6. Here's a little tutorial about the discrete Kalman filter. And I'm going to scroll down to the math. There's a bunch of math. Oh look, the normal distribution. That's a terrible normal distribution. I mean, not as bad as the ones I draw, but normal distribution converges really closely to 0 and doesn't have a nice rounded top like that. Somebody generated that with a really bad vector graphic program. That's not a normal distribution, by the way. So the Kalman filter, this is what we're getting at. In the Kalman filter, there's a predict where you're going to go phase, and then there's a, oh, correct it based on what we see phase. And we repeat. Have you ever tried walking down the sidewalk with your eyes covered and you just keep walking and see how many steps you can take before you accidentally step into the road or onto the grass or something like that? This is basically testing your transition model without the correction phase. You're seeing how well your mind can anticipate where you go. Turns out it's really hard to do it without calibrating. Here's the equations we're going to have to implement, and this is what the Kalman filter comes down to. So we have an initial estimate of where you are. Notice this is given in terms of x, that's where you think you are, and p, this is really the covariance of where you think you are. So these two together make a multivariate normal distribution. You know how a normal distribution has a mean and a variance? Well, the multivariate version has a centroid, that's x, and a covariance. Covariance says how much you vary in all of the dimensions and all the pairings of those dimensions. So a vector and a matrix together make a multivariate normal distribution. And if the number of variables is 10, that means you have a 10-dimensional vector and a 10 by 10 matrix of covariance. And that's all you need to have a normal distribution that spans 10 dimensions, if that makes any sense. So you'll never know where you are. You'll only know where you think you are with some amount of variance. And given that, we're going to first update, meaning we do some action, we think we're here, we did this, and we know that should cause us to go there, but there's noise, which is represented by Q. Q here adds noise to what you did, so it's going to screw up your trustworthiness of your beliefs. But you've still got now some prediction of where you are, given a distribution. And then we have this update phase where we say, oh, now we open our eyes and we look and we see where we are. So the moon's over there, or You open your eyes and say, oh, I'm this far from this edge of the sidewalk. Now we need to update our information by taking how reliable our observations are. And now there's this other indication of noise. I think that's R here. R is how noisy your observations are. So now we can't totally rely on our observations either. The reason this whole thing works is because it multiplies two distributions together. And there's some extra math in there that you have to work out, but fortunately Kalman did it all for us. So we just have to code up his equations. And the result is this is the optimal estimate of state given both your transitions and your noisy observations. And given that, it's kind of amazing how well you can track where you go. Patriot missile depends on it, and any guidance systems that we use depend on it, or some variation of it. And basically, this is what is used in all kinds of branches of engineering for figuring out what the heck is going on, given that you have multiple sources of information. Okay, well, that's it for today, so thanks for coming.